Okay, so we did the complex Fourier series last time. So just to remind you, if a function is periodic, and again, the idea applies for any period, but like the standard period is negative pi to pi, and we've seen in the real Fourier series that if you understand the idea on negative pi pi, then the same idea applies. You can extend it to any period. So if f is periodic of period 2 pi, then the complex Fourier series of f is, so this is the complex Fourier series of f. Again, the advantage of writing the complex Fourier series is just having one form for the series. It's a very simple form with a simple and one form for all the coefficients. So this is 1 over 2 pi, integral minus pi to pi, f of x e to the minus I n x dx. Now, what is the idea of the complex Fourier series? The idea, remember when we started this chapter, the Fourier series, we said that the main idea is if you have a periodic function, you can find approximations using sines and cosines. Now, the idea of the complex Fourier series is that if f is periodic, it can be approximated using the exponentials, using the complex exponentials e to the I and x. So let's see simple, very simple examples, then we move on to make sure we understand everything. So find the complex Fourier series of, for example, if my function is e to the ix plus e to the 3ix minus 4 e to the 5ix. So what is the complex Fourier series? We need to make sure we understand the idea of the complex Fourier series. So the idea is if you have a function, you want to approximate it using complex exponentials. So when we say complex exponentials, we mean e to the ix and e to the 2ix, e to the negative ix, all these powers of e to the ix. So if your function is already having that form, in this example, my function already has e to the ix, e to the 3ix. So in this case, the Fourier series of the function, the complex Fourier series, is exactly the same function. If you agree, it's the same thing, because I'm trying to approximate. For example, if I ask you, I give you a polynomial, and I ask you approximate this polynomial by a polynomial, then clearly the polynomial itself is the best approximation for the function. If I give you sines and cosines and ask you approximate this function by sines and cosines, it's the same thing. And now we're asking about the complex Fourier series, but the concept of the complex Fourier series is to find approximations using complex exponentials. So if your function is already composed of complex exponentials, then the approximation is the same function. Of course, if you try, so let's see what happens. What happens if you try the computations? So again, we are done, okay? The complex Fourier series is the function. But if we didn't see this point, and if someone tries to compute, to do all the computations. What do you mean by the computations? These computations. So if someone says, okay, this is the complex Fourier series, and these are the CN's formula, let's compute them. So how do you do it? We say, okay, what is the CN? It's 1 over 2 pi, integral minus pi to pi, f of x e to the minus I n x dx, which is 1 over 2 pi minus pi to pi. What is f of x? It's e to the ix, 3ix, 5ix, times e to the minus I n x dx. If you expand the bracket, this is e to the I 1 minus n, e to the I 3 minus n, e to the I 5 minus n. right? And now clearly, if you integrate these functions, so we need to start a little before. This is 1 over 2 pi. This is e to the I 1 minus nx over I 1 minus n. E to the I 3 minus n I 3 minus n. For e to the I 5 minus n over I 5 minus n from negative pi to pi. But at this point, I'm sure everybody is seeing this. Everybody is saying, okay, in this last formula, I can't have the n 1 or 3 or 5, right? I can divide by these numbers. So, okay, so this last line is valid only if n is not 1, is not 3, and is not 5. So if n is 2, this is working. But if n is 1, this does not work. So what happens when n is 1? We will see, okay? So this is true only for values different from 1, 3, and 5. Then what is this last thing? So here, this will be exactly 0. Why is it 0? Why is it 0? Let's see. So if you take, so what do we have here? You have e to the I times 1 minus n. What is 1 minus n? N is an integer, right? Because the Fourier series, the n values are from negative infinity to infinity in the sum. So these are integer numbers, whether they are positive or negative. Okay, they can be positive integers, negative integers. But 1 minus n, regardless whether n is positive or negative, 1 minus n is an integer. So after all, you're talking about e to the I in the three terms, in this term, or that term, the power I minus n, 3 minus n, or 5 minus n, they are all positive. They are all integer numbers. So if you say in general, I am x from negative pi to pi, what is this? This is e to the I m pi minus e to the minus I m pi, right? Which is cosine m pi plus I sine m pi minus cosine m pi minus I sine m pi, and the m is an integer. This z represents the integer numbers. We know that the sine m pi is 0. If m is an integer, this is 0. And cosine m pi is regardless minus cosine m pi, and this is 0, right? So if m is an integer, this is the idea. If m is an integer, when you compute e to the I m x from negative pi to pi, it will be 0. So if you go back to the three terms here, e to the I 1 minus n, this is an integer, this is an integer, this is an integer. If you integrate from negative pi to pi, the three of them will be zeros. This is why this whole integral is 0. But again, this integral is 0 provided that n is not 1, is not 3, is not 5. So my conclusion is that Cn is 0 when n is not 1, is not 3, and is not 5. So now the question is, what is C1, right? Then what is C3? Then what is C5? What is C1? We go back to the formula. So C1, if you plug into this formula, C1 is, you replace n by 1. So it will be the integral, and you will have e to the minus ix if you replace the n by 1. So now when we go here, so what is C1? So it will be 1 over 2 pi to minus pi f of x e to the minus ix dx, which is 1 over 2 pi integral minus pi to pi. Now what is f of x times e to the minus ix? You can take it from here, right? So if you replace n by 1 into this formula, you will have, when n is 1, the first term, because n is 1, it will be e to the 0, which is 1, right? So the first term will be 1, plus, when n is 1, the second term will be 2ix. And the last term will be minus 4 e to the 4ix dx, which is 1 over 2 pi. The integral of 1 is 2 pi from negative pi to pi, plus 0 minus 0. Why are these last two terms 0? Because we did the computations here. If you integrate e to the I integer x from negative pi to pi, you will get 0. So in this case it is 0, in this case it is 0. The only exponential that does not give you 0 is e to the 0 ix, which is the constant 1, and in the end you get 1. So now you're saying that c1 is 1. c1 is 1. Now what is c3 and what is c5? Remember, these are the only values that we need to compute. If you compute c3, it will be exactly 1. c5 is exactly -4. What are these values? If you go back, we need to understand all this stuff. If you go back to the general form of the complex Fourier series, in this series, what is the Cn? The Cn is the coefficient. The Cn is the coefficient of e to the I and x. So if you say C1, what is C1? It's the coefficient of e to the ix. What is C2? It's the coefficient of e to the I2x, and so on. So now if you go to this function here, what is C1? C1 is the coefficient of e to the ix, that's 1. And that's what we found exactly after all these computations. We found that C1 is 1. Now, doing the same computations, we didn't do them. But if you do them, what is C3? C3 should give you the coefficient of e to the 3ix, which is 1 in my function. And what is C5? It's the coefficient of e to the I5ix, which is -4. So these are the C's after all. Now once you finish all these computations, so what is the Fourier series of the function? The original form was n from -infinity to infinity, Cn e to the I n x. So now you say, okay, what do we mean by the sum from -infinity to infinity? This means when n is 0, so these are the negative, this is 0, 1, -1, 2, -2, and so on, okay? So when you say from -infinity to infinity, you start with 0. This is the simplest way to do it. You start with 0, then 1 and -1, then 2 and -2, and so on. So basically what is this? This infinite sum is, if you substitute the 0, it will be C0. If you substitute the 1, it will be C1 e to the ix. If you substitute the -1, it will be C -1 e to the -ix. If you substitute the 2, I'm just writing it this way, so the negative are together, the positive are together. Then you say, okay, what is C0? All the C's are zeros, except, remember this, all the C's are zeros, except C1, C3, C5. So the C0 is 0, the C1 is, we found it as 1, so this will be 1 e to the ix, the C2 is 0, the C -1 is 0, the C3 is 1, so the C3 is 1 times e to the 3ix, and the C5 is -4, so -4 e to the 5ix. This is the details behind all the computations. Again, in this example, we did not need to go through all these computations, but this is how it's done, and this is our understanding for the complex Fourier series. So from the beginning, this function is composed of complex exponentials, so I can write the Fourier series right away without doing any of the red computations here, okay? Okay, so let's see another example, another simple example. So this is the first example. The second one, for example, again, I'm trying to find and understand the complex Fourier series. So for example, if my function was cosine x plus e to the 2ix, and let's say cosine square x, and I want to find the complex Fourier series of the function. Again, the complex Fourier series means writing the function somehow in terms of complex exponentials. We already have part of the function as a complex exponential, which is e to the 2ix. But what about cosine square? Remember, the cosine itself can be written in terms of the complex exponential, because cosine x is e to the ix plus e to the negative ix over 2. Then this is squared plus e to the 2ix, right? So if you expand the square, you have 1 over 4 e to the 2ix plus 2 plus e to the, we just expanded the square. And if you collect the e to the 2ix, it will be 1 over 2, this is the 2 over 4, plus 1 over 4 e to the negative 2ix, plus 5 over 4 e to the 2ix, because you have e to the 2ix here, and you have it here. If you collect them, you will have 5 over 4. Again, these numbers, this half, this fourth, this 5 over 4, what are these numbers? The half is the coefficient of e to the 0ix, so this is C0, this is C negative 2, and this is C2. Okay, this is our understanding for this function. Now, if we move to other examples, for example, if we take the function 5 over 2 minus e to the ix. So again, this is a function that we want the complex Fourier series of. And again, the meaning of the complex Fourier series is that writing the function in terms of complex exponentials. In this function, we do have a complex exponential, but it's down in the denominator, while the Fourier series does not have this form. This is the form of the Fourier series. So we want to write this somehow as a sum of complex exponentials. So the idea in this example is a little different. The idea is, if you look at this, this is 5 over 2, 1 minus e to the ix over 2, right? Which is 5 over 2. This quantity, it reminds me of something. This 1, this is 1 over 1 minus something, right? And if you remember 1 over 1 minus x, this is the sum of the geometric series, right? It is a geometric series, the sum of x to the n, and from 0 to infinity, of course, provided that the absolute value of x is less than 1, okay? In this example, if we find the absolute value, so after doing the example, we will find the absolute value of e to the ix over 2, and it has to be less than 1 in order to apply the geometric series idea. So if you apply the geometric series idea, what is 1 over 1 minus e to the ix over 2? It's the sum, and from 0 to infinity, e to the ix over 2 to the n, which is the sum. If you insert the 5 over 2, 5 over 2n plus 1 e to the I n x. So this is the Fourier series, the complex Fourier series of the original function. Now again, if we just, to make everything clear, if we compute the absolute value of e to the ix over 2, first of all, the half is a constant, so it goes out. What is the absolute value of e to the ix? This is half. What is e to the ix? It's cosine x plus I sine x. And remember, this is a complex number. If you have a complex number, how do you compute the absolute value? It's the square root of cosine square plus sine square. It's the root of the real part square plus the imaginary part square, which is half times 1, which is half, which is less than 1. So because it's less than 1, we can apply the geometric series idea. This is how we find the complex Fourier series of this function. So these are like some basic examples about our understanding of the complex Fourier series. Now usually when we find the complex Fourier series, we go through the integrals. So in these examples, we haven't gone through any integral. But in general, for example, if my function is x and x was between negative pi and pi, and remember please, these functions, as long as we're talking about the Fourier series, these functions are periodic. That's understood implicitly without saying. This means the function is extended this way. Even if we don't write this last line, we understand it implicitly. So if we want to find the complex Fourier series for this function, how do we do it? We just find the Cn. And again, the Cn formula is this. You replace f of x by x. And now this is an integral that we need to do using integration by parts. So if we do the integration by parts, this is u, this is dv, the u is x, the dv is e to the minus I n x, differentiate. Now when you integrate the e, it's the same, but you divide it by the coefficient of x, then differentiate again, integrate again. When you divide again by negative, the negative gets cancelled, but the I becomes I square, which is negative, and the n becomes square. Then you multiply diagonal and diagonal, right? So plus, minus, plus integral. So now what's this integral? It is 1 over 2 pi times you copy that integral, so it's minus x e to the minus I n x over I n, then plus e to the minus I n x over n square from negative pi to pi. And now you substitute. This is 1 over 2 pi times, when you substitute the pi, you get minus pi e to the minus I n pi over I n, plus when you substitute the pi again, e to the minus I n pi over n square. Then minus, now you substitute the negative pi, which gives you pi e to I n pi over I n plus e to the I n pi over n square. Now what is, we need to remember these computations. So what is e to the I n pi? E to the I n pi is cosine n pi plus I sine n pi. But we know that sine n pi is always 0 and cosine n pi is negative 1 to the n. The nice thing, if you compute e to the negative I n pi, it's the same thing. E to the negative I n pi, it's the same thing. So basically when you do these computations, e to the I n pi over n square, it gets cancelled with e to the negative I n pi over n square. So what is left? Here you have negative pi and negative pi. So you have 1 over 2 pi times, you have I n as a common factor. E to the I n pi is negative 1 to the n, and you have negative 2 pi from negative pi minus pi. So in the end, this is the 2 is cancelled, the pi is cancelled. So the final thing is minus 1 to the n plus 1, right, over I times n. So this is our Cn. I told you before that we don't like seeing the I in the denominator. So this I down, we don't like seeing it there. We must have it up. So how do we have it up? We multiply with I over I. That gives us an extra negative sign. So the I becomes in the numerator, but then we will have negative 1 to the n over an I. This is the Fourier coefficient of the function x. So after finding this, we are ready to write the complex Fourier series. But again, at this stage, I'm sure that everybody is looking at this formula and is asking, but this formula does not work when n is 0, right? When n is 0, you can divide by n. From this step here, these computations are all not valid when n is 0. So when n is 0, we need to do it alone. So now, when n is 0, we need to compute C0, which is 1 over 2 pi integral negative pi to pi f of x e to the minus I0x, which is 1 over 2 pi integral, the f of x is x and e to the 0 is 1, so the integral is 0. So now we are done. So we found these are the Fourier coefficient. These are the Cn's when n is not 0, and this is C0. So now what's the Fourier series? It is the sum from negative infinity to infinity, Cn e. But this is, what is the Cn? What is the Cn? It is exactly this. So it's negative 1 to the n over ni multiplied with e to the I n x. Fine. So this is the Cn. But this is not true when n is 0. So this is true only when n is not 0. After that, we need to add what happens when n is 0. But when n is 0, C0 is 0. So in the end, we have from negative infinity to infinity, but n is not 0, negative 1 to the n over ni e to the I n x. This is the final form of the Fourier coefficient, of the Fourier series of the function x. This is the complex Fourier series of the function x. If you compare this, just back, and if you compare this with when we found the real Fourier series of the function x, if you remember, it was the sum from 1 to infinity to -1 to the n plus 1 over n sine n x. If you remember, this is what we found as the real Fourier series of the function. So now, to conclude this example, I like to comment on the function f of x equals x. So what is my comment? We know that the real Fourier series is the sum from 1 to infinity. Again, we found that this was one of the first example that we solved on the Fourier series. And now we're saying that the complex Fourier series of the function is the sum from -infinity to infinity, but n is not 0 for this new form. So -1 to the n over ni e to the I n x, right? So in this example, I want to show you that the two answers are the same, but they are written in different ways. In fact, I don't need to show you this, because when we started the complex Fourier series, we deduced the complex Fourier series from the real one. So we should understand that the two series are the same, but they are written in different ways for different applications. But let's see the computations. So if we take this complex Fourier series and say, okay, let's simplify it, okay? So we're adding all integers from -infinity to infinity, but when n is not 0. So to avoid this, let's say we're adding from -infinity to -1. Then we're adding from 1 to infinity, right? Okay, let me do it here. And now expand the sums. So what happens? If you take in the first sum, please, in the first sum, I'm substituting -n for n. So I'm going to each n, replacing it by -n. I can do that by substitution, but then n will be from 1 to infinity. So basically what I'm doing in the first sum, I'm taking -n as k. But again, in the summand, you can write n or k or t. The notation is irrelevant. So simply, we just replace every n by -n, but in that case, you need to switch the limits. Instead of having them from -infinity to -1, they must be from 1 to infinity. You multiply them with negative, basically. Okay, then plus, this is the second sum. And now, because both sums start and end at the same numbers from 1 to infinity, I can have one sum for all. So we have one sum from 1 to infinity. The I, you can take it out as a common factor, and you will have inside the summand, what is -1 to the -n? Basically, -1 to the -n is -1 to the -1 all to the n. But -1 to the -1 is just -1. So basically, this is -1 to the n. So you're dealing with -1 to the -n and -1 to the n. In fact, they are the same number. So you can factorize this term. So you'll have -1 to the n as a common factor, over n as a common factor. The I, we already took it as a common factor. So what's left? From the other sum, the second sum, you have e to the I n x, right? Minus, why is it minus? Because we have a minus sign here. So minus, from the first sum, you will have e to the minus I n x. So let's delete these computations here. And now what is this? This is the I again. This is the sum from 1 to infinity, -1 to the n over n. What is e to the I n x minus e to the minus I n x? It is 2I sine n x, which means now if you multiply the I, you have an I here and I here. I times I is -1, and you already have -1 to the n, so together you will have negative 1 to the n plus 1. You have the 2 times sine nx, which is identical, and this is what we are trying to show. This is identical to what we found in the beginning of this chapter, that the Fourier series of the function x is this. So basically, please, what we did in this comment is we started with the complex Fourier series, and we've shown that this complex Fourier series is exactly the real Fourier series. So the two series are the same. They are written in different ways for different applications, and that's it.